Hi, I'm Jeff Applebaum. Welcome to the Cadence Innovation Theater at the 58th Design Automation Conference. In this video, we begin with Senior Vice President Chin-Chi Tang on the latest news in machine learning applied to chip design. We conclude by highlighting the impact of machine learning on chip design. And now, here's Chin-Chi.
Welcome and thank you all for joining us today at our event. We are driving a new era in electronic design powered by machine learning technology. This moment is a result of over 40 years of innovation, applying artificial intelligence to chip design. The semiconductor industry is experiencing a renaissance. Truly extraordinary change is taking place right before our eyes. We see strong growth in 5G, autonomous driving, industrial IoT, and hyperscale compute. Underlying each of these trends is the application of machine learning and artificial intelligence. All the new applications and the technology interdependency are driving demand for even more compute, more functionality, and the faster data transmission speed. Everyone in the semiconductor industry has to push to deliver their next generation product into market even sooner. I've met with a number of you discussing the challenges and the complexity you are facing developing your next generation product. These devices are incredibly complex, with some leading edge design reaching 2 billion gates of logic, using the most advanced packaging architecture and implement on 7 nanometer, 5 nanometer process node, eventually even 3 nanometer or below. So how can we expect the design team to succeed when the design complexity exceeds the hour of the day needed to implement in silicon? How can design team squeeze out every possible margin and optimize for the best possible performance, power, and area? These challenges are daunting. Just put more resources on the problem or working harder does not really scale. Not to mention, hiring a good engineer from the market is even more challenging than ever. So how Cadence can help? The EDA industry has enabled silicon design to evolve through a series of the designer productivity advancement, from drawing logic in the customer tools to synthesizing logic from RTL and automated place and route. Every and each step of the way enabling a new generation of electronics and end product productivities. Again, we are now at the beginning of the new era of electronic design automation. Using machine learning technology, we are delivering a first of its kind, scalable, automated digital design flow from RTL to GDS that enable any designer to achieve their PPA goal much faster and easier, like autonomous driving for chip design. The system can deliver improved PPA and design quality. It also can learn from the previous project to guide the future project to success. The system also uses a massively parallel architecture, perfectly designed for the distributed computing in the cloud. Ladies and gentlemen, introducing Cerebrus, the future of intelligent design is here. Let's take a quick look. I have to say, that is very exciting. The Cerebrus Intelligence Chip Explorer uses a unique reinforcement learning algorithm that can optimize multiple steps in the design flow simultaneously, but not just one, so that it can help to overcome the growing complexity of the design at the 7 nanometer and below, enabling 10x engineering productivity with massive cloud scalability and producing better PPA. You also can help the K team to develop an optimized RTL to GDS digital flow for their design team to use. You also can help the foundry team to concurrently optimize design and technology.
I'm a part of design technology team at Samsung Foundry, and one of our key objectives is to develop leading-edge digital implementation flow for the latest Samsung Foundry processor nodes such as 4 nanometer and 3 nanometer. This optimized flow was used internally by Samsung Foundry to validate new processor node, PPA, and deliver to customers, enabling them to quickly start design projects. A great feature of Cerebrus is it can be easily configured to optimize for any user-defined goal. This allowed us to define flow optimization scenarios for different power mesh configurations, things like different wire width, spacing, layers, and via types. Compared to our manual developed flow, the Cerebrus optimized power delivery network shows over 50% better timing and improved power result. This proved to be a great example of how Samsung Foundry can use Cerebrus to automate part of the DTCO development. Cerebrus automatically run over 8 different flow optimization scenarios on a number of distributed computers, and in a few days, converged with over 8% better power and over 2% less area. Compared to our manually tuned flow, this was a big productivity improvement for the whole engineering team. It has been great to partner with Cadence on this new machine learning driven for flow optimization development. Based on our experience, Cerebrus delivering better PPA much more quickly than we can achieve manually. Samsung Foundry will be using Cerebrus for our DTCO and customer design project.
Cadence, we empower engineers at world-leading semiconductor and systems companies to create intelligent and highly differentiated electronic products that rely on the most advanced semiconductor devices. From consumer products like mobile devices and autonomous driving to next-generation hyperscale computing, the technologies of the future will be integral in our lives and intelligently connected. Electronic design automation, EDA, has always been at the forefront of breakthrough design, driven by advanced computational software, the bedrock of what Cadence delivers. With the explosion of big data and massive computational workloads, it's more important than ever to leverage proven software, computational in nature, that includes best-in-class design, verification, IP, and system analysis capabilities. Recent advancements in silicon design and computational software address these design challenges head-on with an intelligent dimension. The difference centers on select key innovations: integration and co-mingling of previously independent design, analysis, and implementation to achieve optimal results. Partitioning and scaling of computation to thousands of CPU cores and servers. And the introduction of machine learning to improve and harness design heuristics for system optimization. Today, most large system-on-chips are designed at the RTL level, using System C, C, or C++ as the programming language, with high-level synthesis and various forms of verification, from simulation to emulation and formal. These enable designers to create and debug designs and automate the process of transforming the high-level descriptions to low-level implementation required for manufacturing. To counter the growth in design size, complexity, and computational scope, algorithms now utilize multiple CPU cores. This approach enables early software development and system debugging, analysis, and modeling before the chip is manufactured. Another key facet of computational software is at the system level. The complexity of systems requires co-design and co-optimization of the semiconductor with its IC package, PCBs, connectors, and cables. Multiphysics simulation is now a necessity for system design. One example is high-speed data communications, which have data rates up to 112 gigabits per second that require analysis tools connected to those environments to deliver automated selection of optimal system implementation decisions. Design tools and designers often apply recipes or ordered sets of steps when applying computational algorithms to their design challenge. Machine learning is particularly good at large-scale, pattern-based algorithms and is implemented with the same matrix analysis technology found in EDA and system analysis. By evaluating and learning from successful prior designs, Cadence tools can evaluate thousands of possibilities, and the best outcome can be selected. By focusing on the system-level requirements and employing machine learning to optimize decision-making, Cadence's computational software know-how gives engineers the ability to create the intelligent electronic technologies of tomorrow. Cadence, computational software for intelligent system design.